In this lesson, we're going to look at functions. Thus far in the course, we've talked about equations with one variable, we've looked at the graphs of equations with two variables, and now we're going to jump on to the idea of what exactly is a function. And a function is very similar to the graphs with two variables that we were looking at before, but a function has its own meaning in its own right. First off, let's just talk about a relation. Now, a relation is simply a set of ordered pairs. While that doesn't really mean a lot in the context of what we're doing right now, we can say, okay, well, some set of ordered pairs, and what we want to do from that is come up with a new idea of what a function is. Relation's a set of ordered pairs. Could be infinite, just a set of ordered pairs. We'll talk about more of this in a moment. The domain of the relation is all the first coordinates, and you can think of them as the x-coordinates if you'd like. And the range is all of the corresponding y-coordinates. It's the set of all of the y-coordinates, the second coordinates if you will. We've got x values, we've got y values, and let's just take a quick look at this. For the first function, the domain is, using these curly brackets, let's see, we've got 4, 7, 3, and 7's a duplicate, so I'm not going to include it twice. So we just talk about the set of the first coordinates, or the x values if you'd like. And the range is the set of all corresponding y-coordinates. So it looks like we get 5, 3, 6, and 5 is another repeat, so we won't include that. For g here, the domain is just -2, -4, and 0. There's no repeats this time. For the range, we get 3, -3, and 0. So these are our setup for these relations. The x-coordinates are the first coordinates. If there's any duplicates, we don't write them down. And the range is all the second coordinates. Let's try this when there's infinitely many points. Now this is not just a finite set. You could talk about any point in here, not necessarily just the ones that appear at x values of integers, but this whole smooth curve is an infinite set of points. So in this case, we can talk about the domain and range, but we can't list the elements in the domain and range. Yes, it does start from x equals, looks like -5, and it goes up to x equals +6. But all the values count in there. So -4.5, -4.1, -4.01, so on. All of these values are in the domain of the function. So when we do domain for an actual graph, we'll use intervals. So as we said, from -5 to 6, there are x values. So let's write that as the interval, -5 to 6, and I'm using brackets because there's actually points at these locations. Next, the range. The range is all the y-coordinates here. It looks like the smallest y-coordinate is -5. And the largest y-coordinate is +5. So that's your domain and range. The next example. Now this graph appears to go to the left forever by paying attention to these arrows. If it's going to the left forever, then I'm going to say the domain, all the x values are out to -infinity. But they do stop. If you look at the x-coordinates, you see that they stop at 3. And there's a bracket there because that's actually a point on the graph. And then we've got the range. The range is the set of all the possible y-coordinates. And just looking at the shape of this graph, it does look like it will appear to rise forever and also to go down forever. So we get all the y-coordinates. Any possibility, we'll write that as -infinity to infinity. Now that we've talked about relations, let's talk about functions. In the first example of a relation we did, we had some repetition. Some repetition's okay if it's in the range, but a function is a special idea. The whole point of a function is that it takes something and gives you an output. It takes an input and gives you an output. The idea of a function is that the output should be predetermined. If you take one particular input, you should get the same output every time. There should be no question of what the output would be. It's kind of like if you stick water in a freezer. If you didn't get ice out of sticking water in the freezer, you would question your existence. You need the function to always have the same output. With that said, we've got 4, 2, 5, 7, 3, 8, and 4, 6. What I notice is the number 4. shows up twice with different outputs. That's a problem. So let me say this. Let me draw it like this. And I'm going to use this arrow to mean maps to. Since 4 maps to 2 and to 6, again, only one output can be associated with a particular input, not 2. We only need 1. This is not a function. And here's your shortcut also. If you're doing just ordered pairs, you can just look at the 4s and say, oh, that repeated with different values, not a function. So in general, if you have repeated values among the x-coordinates, then you can immediately say it's not a function. Next one, I have 3, 2, 7, 4, negative 3, 2, and 1, 4. Now no x-coordinate is repeated, but there is a y-coordinate repeated. The 4. 7, 4, and 1, 4. But that's okay. You can have an output that shows up with 2 different inputs, but you cannot have an input that shows up with 2 different outputs. Repeated x-coordinates mean not a function, but repeated y-coordinates are okay. Function, since every input yields 1 output. If we want to know that a graph is a function, we have some shortcuts. We talked about the ordered pairs. You can just see if there is an x-coordinate repeated. If you're given a graph, though, all you have to do is what's called the vertical line test. If you are able to draw a vertical line that passes through more than one point, it's not a function. That's because that vertical line has the same x-coordinates but passes through more than one point. That's an x-coordinate with more than one y-coordinate associated to it. So that immediately means not a function. Similarly, though, if every vertical line only crosses through one point, that's a function. For example, the first one, not a function. There's a vertical line that passes through both points. Second one, every vertical line I draw passes through only one point, so that's a function. Now you can probably look at the third one and you'll already know the third one is not a function because the vertical line test fails. It passes through more than one point. Next thing to pay attention to with functions is often we create a notation for these. And this notation is called f of x. Now you've probably run into this in your mathematical career, but it's called f of x. F of x tells you the independent variable. It tells you the variable that's being used as the input is the x variable. X is my input. F is just the name of the function. And then what comes out of it is what we call f of x. You could even think of it as y. So instead of writing y equals something, we could write f of x equals something. So y and f of x are basically interchangeable. Just one notation is very nice. I should also add another nice use of this is when you have f of x and you plug in a value for x, you can write it as, say, f of 2, just that value. But let's take a look at this. We've got the function y equals 3x minus 4. In the previous chapter, we determined that was the equation of a line. We could have graphed it. But now I want to think about it as a function. X is my input, and y is my output. F of x equals 3x minus 4 is my function form. With that said, f of 3, what that means is x is changing to 3. Instead of x being my input, 3 is now my input, and I get 9 minus 4, which is 5. Very, very convenient way to do this. It's very helpful to be able to just use a quick notation for what it means to plug in a value. Let's do a couple of examples of writing these things as functions. What we need to do is solve for y, so we can say y equals f of x, and then we'll evaluate it at 3. So for the first one, let's get y by itself. I get 5x plus 4 equals 2y, and if I divide by 2, I get y equals 5 over 2x plus 2. That's our linear equation form. If it's a function, I get f of x equals 5 halves x plus 2. And then the second thing they asked for was evaluated at 3. Well, that's f of 3. That's 5 halves times 3 plus 2. I get 15 over 2, and I'll get a common denominator of 4 over 2, so I get 19 over 2. So those are our function and the value when you plug in 3. B is a little bit easier. All I need to do to solve for y is subtract 2 from both sides. I get y equals x squared minus 2. Nothing combines, but I do get y equals x squared minus 2. So let's call this g of x equals x squared minus 2. Now you can use whatever name you want for a function. F of x, g of x, h of x. You could use capital letters. Those are the most common ones, are f, g, and h. But you might see others at times, like if a variable represents something, you might use the first letter in the word for it, and so on. Anyway, so there's your function form. And then they want us to calculate g of 3, so I get 3 squared minus 2. That's 9 minus 2, which is 7. Function notation is very useful because whenever I write it with function notation, I have a clean, easy way to say what it means to evaluate at x equals 3. Next example. If I want to solve for y here, let's just add y to both sides first. I get the square root of 2 minus x is equal to y plus 5. And then if I subtract 5 from both sides, I get y equals... Now this is where people mess up sometimes. I'm not going to subtract inside the square root. The square root is hanging out by itself. It's not a like term with that 5. So I get the square root of 2 minus x minus 5. Just giving it another name, let's call it h of x. Well, that's my function. 2 minus x minus 5. If I plug in 3 one more time, I get square root of 2 minus 3 minus 5. And that's the square root of negative 1 minus 5. And I will say, most of the time when we do functions, we want real numbers for our output. With that said, really this function's not defined at 3. You would just say undefined. But since we have it, I might as well just call it I. But I'm going to stick with undefined as a real number. The final topic in this section is how do we calculate the domain of a function when it's given to us as an actual equation. Normally we really don't know exactly what the domain would be based on if it's not given to us, but we can come up with what would a reasonable domain be by just picking out what would the domain be for any value that is reasonable. By reasonable, I mean it would be a real number. It would make sense to talk about it. Some things in the two main ones that you should focus on is if there's a 0 in the denominator or a negative square root. This is important. Denominator being 0, and square roots being negative. You can't have these values in a real valued function. If you want to get a real number, you can't divide by 0. You can't take the square root of a negative number. What we need to do is look and see, well, do either of these things occur? X plus 3 is in the denominator. If that thing were 0, I'd have a problem. Let's just set up a simple equation. And rather than equal 0, I'm going to say it can't be 0. But I'll solve it the same way by subtracting 3. And I see that x can't be negative 3. All the other values of x are fine, but if x is negative 3, I get a 0 in the denominator. With that said, I'm going to write the domain as negative infinity to negative 3 union negative 3 to infinity. That's my interval notation for it. And just to give you a little graph as to where I got that from, if I need to remove negative 3, well, I'm going to get everything to the left of it. Don't include it, but then I'll pick right back up at negative 3 and keep going and get everything else. So all the real numbers but negative 3 look like this in interval notation. Next example. X minus 4 is inside of a square root. Now we can't have a negative square root. If x minus 4 can't be negative, then x minus 4 will be greater than or equal to 0. With that said, add 4 to both sides and I get x is greater than or equal to 4. And that's it. There's really nothing else to look at, but as long as x is at least 4, I'll get a non-negative number inside of the square root and it'll be defined. That looks like 4 with a bracket to infinity in interval notation. Just to summarize this, this is what we do. If we set the denominator equal to 0 and exclude these values by using the not equal to symbol, that's what we do every time we see a denominator. To go a little further, every time we see a square root, what we do is we take the inside. Keyword here is inside, not the whole square root, but the inside of the square root. Set that greater than or equal to 0, and that's your domain unless you have to take something out from the denominator. But let's try to do one that's combined. We've got the square root of 2 minus x divided by x plus 1. First off, x plus 1 can't be 0. So x can't be negative 1. That's the 0 part. Since we had a denominator, we have to fix it so that the denominator is not going to be 0. Next, we look at the square root of 2 minus x. 2 minus x can't have a negative, or else you'd have a negative in a square root. So every time I see a square root, my rules say set the inside greater than or equal to 0. So 2 minus x is on the inside, greater than or equal to 0. If I subtract 2 from both sides, I get negative x greater than or equal to negative 2. And dividing by a negative, I get x and 2, but I need to flip the sign. So let's definitely draw the picture first. I've got x less than or equal to 2. And I'm coming along this way, but x can't be negative 1. That means I got to stop at negative 1 and restart, coming back from negative 2. So reading this left to right, I have negative infinity to negative 1 parentheses, union negative 1 parentheses, 2 bracket. That's the domain of this function. This last one is for you to try. Feel free to pause the video real quick and just do an example of it, and then I'll come back and help you with it. Okay, let's do the same thing that we did last time. Well, since x is in the denominator, that means x can't be 0. That would cause a problem. And then we've got x plus 1 inside of a square root. Well, that means that x plus 1 has to be at least 0, and consequently x has to be at least negative 1. We've got not equal to 0, we've got greater than or equal to negative 1, and let's just draw the picture and find it in interval notation. Negative 1 and 0. So x has to be greater than or equal to negative 1. So we'll come along, but once we get to 0, we have to exclude it. And then we'll continue on after 0 as before. The interval notation is negative 1 to 0, union 0 to infinity.